We're going to talk about some of the early atomic theories and how we have come to our current model of the atom. Chemists have strived to understand the nature of matter through a combination of gathering and analyzing evidence, creating theoretical concepts to explain this evidence. And many of these men can be attributed to our current understanding. Note that in this lesson, there are lots of success stories and failures that have happened. However, I can only document a few of them, but note that many of these chemists that we're going to be talking about and physicists have gotten to where they are due to some of the success and failures of many others. Let's start off with around 492 to 375 before Christ era, when Aristotle and Plato, who are very famous philosophers, postulated that there were only four types of elements that existed. And again, remember that they are coming up with this based on deductive reasoning. Around them they see that there's earth and fire and water and air, and hence why would not everything be made up of those four elements? Their idea is that everything in and around us were made up of these four elements, held true for about 2,000 years. So this is what they would think. If you take a little bit of each in different combinations, they would equal the things around us. So a bunny rabbit would be equal to taking a little bit of fire, air, water, and earth. It seems quite absurd, but at the time, that was the thinking, and I guess you have to start from somewhere. In and around 440 BCE, Democritus came up with a theory that as you broke down materials into smaller and smaller particles, eventually you would get to a particle so small that you could not break it down any further. So for instance, if you were to take a piece of clay, you would cut it in half and then cut it again and keep cutting and cutting and cutting. There comes to be a point where it is no longer cuttable. And at that point, he called that the atom. Or you would take a piece of matter and keep pounding it until it could no longer be pounded any further. And you would come to a particle known as an atomos, meaning an atom in Greek, standing for indivisible. Democritus thought that these small particles made up everything in and around us, and that they comprised of different shapes based on the properties that they had. So for instance, water would be like smooth round balls because they were pourable. And you would have, perhaps fire was sharp edges were those particles. And iron would have little jagged spikes because they were magnetic. Then along comes Dalton, which is about 2,000 years later. You've got this British scientist who re-erects this idea of the atom, and his work was really based on scientific evidence, not just reasoning like the other two who were philosophers. He kept what Democritus had said, were that atoms were the smallest building blocks of matter. And in chemical reactions, atoms are neither created or destroyed, only rearranged differently. And that was with the help of another scientist known as Antoine Lavoisier. So you may recall in grade 10 when you did an experiment where you had to take the mass of the reactants before a reaction, mix the two together, take the mass after, and you would notice that the mass of your products equals the mass of your reactants. Hence, we cannot destroy or create matter. He also stated that atoms of the same element are identical. They have the same properties such as mass and size. So if you were to have a piece of gold foil, all of the atoms that make up that gold are the same, and they would differ from, let's say, a piece of aluminum foil where all the atoms are aluminum. So we know today that that is not entirely true, as we now have isotopes, which are essentially atoms of the same element. They just differ in their number of neutrons, which means that they do differ in mass. And lastly, he did say that atoms of different elements can combine to form compounds in specific proportions. Dalton pictured that these atoms were more like little round spheres. They weren't different shapes as Democritus had stated. And he is attributed to the billiard ball model of the atom being a little round sphere and basically, at a much smaller scale. He also created a table of elements that had symbols to represent each of those elements. Thompson's model in and around the late 1800s provided a little bit of information that the atom actually can be divisible into smaller subatomic particles. And so he is famous for his cathode ray tube experiment, where he has a gas tube that is vacuum sealed, and you would pass electricity through this tube. The tube is coated with a fluorescent zinc oxide coating so that you could detect the passage of electricity moving through it. What he then did was he applied a magnetic field to his cathode ray tube, so the blue beam representing the passage of electricity. He would take a magnet, and the north end of the magnet represents the negative pole, and he noticed that the beam of electricity would move away, it would repel. And when he turned the magnet to the south pole, the positive end, he noticed that the beam of electricity actually attracted. So what this indicated to us that there's something about these atoms that is causing them to attract and repel. And what he had discovered is that the atom actually contains negatively charged particles. So this particle he actually found was much, much smaller than the hydrogen atom, and the hydrogen atom being the smallest atom. So when he did a mass ratio, he noticed that there's something that is much smaller that existed within the atom, and he discovered the electron. At the time, they were referred to as corpuscles, but today we call them electrons. So he envisioned the model of the atom to be much like a cookie or a blueberry muffin, or at the time, the plum pudding model. We don't tend to eat plum pudding anymore, so it's more apt to refer to it as the blueberry muffin model or the chocolate chip cookie model. He envisioned that the atoms are still spheres with, positive charge that was uniform throughout, and the electrons were distributed throughout this positive sphere, much like the chocolate chips in a cookie, and those negatives would counterbalance all of the positive, making the overall atom neutral. This here, the most of the mass of the atom is located where the positive portion of the cookie or that sphere would be. This brings me to Rutherford, and Rutherford, in and around the early 1900s, was starting to unravel some of the mysteries of the atom, because we had, radioactive materials that were available, and people were sort of playing around with that concept as well. So what he did was he devised this gold foil experiment, one in which he takes a piece of gold foil that is comprised of many gold foil atoms, and he essentially took alpha particles, radioactive particles, and he would shoot those particles at the gold foil. What he discovered was when he shot these beams of alpha particles, that 1 in 10,000 would reflect or deflect straight back. This was, crazy to him, because this was like thinking that you had a piece of tissue paper and you would shoot a gun at the tissue paper and the bullet would come right back at you. This was not supposed to happen. So as I had mentioned, due to the fact that Thompson's model, if it was correct and the mass is evenly distributed through, all of these alpha particles should have gone straight through. So why did they deflect and reflect? Well, what was happening was those alpha particles must have been hitting something, and they were hitting a very dense core. Now, the probability of hitting that core obviously was very small. It would be equivalent to the size of a fly in the middle of a football field. So very, very small. But yet we discovered now the nucleus. The nucleus is where the mass of the atom is located, and the majority of these alpha particles went through, because we have discovered now that the atom is not a solid little sphere. What we have figured out, it is mostly empty space with a hard core nucleus in the middle. Now, we also can attribute, some other work to other scientists like Chadwick, who discovered the proton, and then we also have the discovery of the neutron as well. We're not going to be getting into that, but just know at this point in time, we have a nucleus with some electrons. Now, where are these electrons? Because they were discovered by Thompson, Rutherford just said that they were hovering around the atom like bees around a hive. Now, A limitation to Rutherford's model is something to do with what scientists and physicists had been thinking, was that, if we have these electrons that are constantly moving around, changing speed and direction, they should be, producing light. And when they emit this light and energy, they should lose that energy and spiral into the middle. And if they weren't doing that, if they were just stationary, then the positive charge of the nucleus, due to the protons, should be attracting the electrons and everything sort of should be collapsing. We know that that does not occur, as everything in and around us is stable. So there's something else at play.
It was known that a proton and any atom were grouped in a small central region called the nucleus, and that the electrons were somehow arranged in comparatively large distances outside the nucleus. But in hydrogen, if the electron were stationary, it would fall into the nucleus, since the charges on the particles would cause them to attract one another. Yet the electron couldn't be in orbit circling the nucleus either. Circular motion requires consistent acceleration of circling body to keep it from flying away. But the electron has charge, and charged particles radiate light when they are accelerating. So an electron in a circular orbit would radiate light and would spiral into the nucleus.
So along comes Niels Bohr in around the 1914, a Danish physicist, and he actually, through the study of light, was able to improve Rutherford's model. So what is light? Well, light is an electromagnetic radiation that travels through space in wave-like oscillations. Sometimes we refer to light as a wave, and sometimes we refer to it as a particle when we talk about it being a photon. Certain characteristics of light that you may have heard of in physics class is that light has a certain frequency, wavelength, and an energy associated with it. A wavelength is from one particular point to a similar point on a set of waves. So from a peak to another peak, or we call that a crest to another crest, is considered to be a wavelength, or from a trough to another trough. So from one valley to another is considered to be a wavelength. When we're talking about frequency of light, it's how many waves happen over a given period of time. So when you have a large number of waves given over a period of time, we would say that that particular light has high frequency. Now, when we have high frequency light, we associate high energy with that particular wavelength of light. So what happens when we look at an electromagnetic spectrum? You have the visible spectrum, which we are able to see. So we are able to see the colors of the rainbow, Roy G. Biv: red, orange, yellow, blue, indigo, and violet. And the wavelengths of those light are between 400 and 700 nanometers. Now, when we look at shorter wavelengths, we're talking about gamma rays and X-rays. They have very high frequency and high energy. So wavelength and frequency are inversely proportional, as well as the energy. And then when we have longer wavelengths of light, we have lower frequency and we have lower energy. Max Planck, or Planck, however you want to pronounce it, he was doing a lot of work with Einstein at the time, and they were also studying this concept of light, in that photons did carry a certain amount of energy. And so we can attribute a lot of our current understanding of the atom to his work. If we had more time, we would be looking at different calculations involving frequency and wavelength with the speed of light and calculating energy of light. But unfortunately, we don't have time to do that at this point. Niels Bohr was also looking towards what Planck and Einstein were doing. And he knew that elements gained energy, that they would release that energy in specific amounts. So you may recall doing a flame test in grade 11 where you would subject different elements to the flame, and the atoms of those elements would become excited, and we knew that they would emit a certain color. And you could figure out an unknown element based on matching it to known flame colors. If we take this one step further, what we can do is we can take that flame color and we can subject it to a prism or diffraction grating or what's known as a spectroscope. And when we take a look at that flame color through a prism, we would notice that it would either yield a continuous spectrum if it was white light, or it would yield an emission spectrum, a unique series of colored lines that was only specific to each element. So it really was like a barcode or a fingerprint that helped to identify what the element was. So what we can also do is we can use a gas discharge tube. So in these tubes, they are vacuum sealed with a given gas. And what we can do is we can pass electricity through it to see the color that they give off. And then in doing so, we can use a diffraction grating to take a look at those colors.
Is to place this diffraction grating in front of a camera and show you the view of this continuous source with a diffraction grating in place. And what you'll see in the image is the image of the incandescent bulb itself, and then to the right and to the left you'll see a rainbow spectrum that shows what wavelengths are present in this. You'll see, as you look on the right side, violet through all the colors of the spectrum, all the way through red. What this is it's a discharge tube. It has mercury in it, and what I'll do is energize this tube, apply a voltage to the tube, and that causes the gas in it to emit spectral lines according to the spectrum of the element that we're using, in this case mercury. This is a mercury spectrum without the diffraction grating. Let me get it in focus here. It's a bluish colored spectrum. There are mercury vapor lights that are used as street lights. So this may look similar to this bluish tint to the mercury vapor. Now let's try it with the diffraction grating in place. And what you see in this case are a green line and a blue line predominantly in this mercury spectrum. So this is nitrogen spectrum. And with the diffraction grating in place, we see a number of lines present, some red, orange, yellow, green, and a violet turquoise-ish colored line. So this is hydrogen. It has a reddish cast to it. And when the diffraction grating is in place, you'll see three lines. The farthest from the central image is a red line. That's the hydrogen alpha line. And it is very important in star images. A lot of nebula in the sky have hydrogen alpha line as one of their prominent spectral lines. Then there's a turquoise colored line, greenish blue is the hydrogen beta line. Both from the Balmer series, and we'll talk about those, or have talked about those in class. And then finally, the hydrogen gamma line is a violet line, is generally considered to be the one that's, those three lines are visible in the hydrogen spectrum.
Now, in his mid 20s, Niels Bohr actually went to Cambridge University in England to join the group working under J.J. Thompson. And at the time, Thompson's group was attempting quite unsuccessfully to explain the electrons and atoms and this atomic spectra. And Bohr had suggested that tinkering with this model would never work and that some revolutionary change was required. And Bohr's hunch was that a new model required using the new quantum theory of light developed by Planck and Einstein. Thompson did not like these revolutionary ideas, especially from a young guy fresh out of university in Denmark. And they had many heated arguments. And so Bohr decided to abandon Thompson's group in Cambridge, and he actually went to the University of Manchester to work with Rutherford. And it turned out to be a much better environment for him to develop his theories. You know, Rutherford's description of the atom couldn't account for some of these observations. So, a second limitation of Rutherford was that if the electrons were actually just sort of hovering around at any distance, then the light emitted from them should be spread evenly across the electromagnetic spectrum, and every element should be producing a continuous spectrum, just like we saw with the white light. But that was not the case. So Bohr decided to, work primarily with hydrogen. Why not start there? It's the smallest atom. And to try and explain the bands, the colored bands that he saw within the line spectra. So what he proposed was this planetary model of the atom where the electrons, he said, were found at discrete distances. So he reasoned that, if the light was being released at these certain wavelengths, then electrons can only have certain energies. Just like a gearbox in a car can only have certain gears, like first, second, or third, he said that the simplest arrangement would be a planetary model with each electron orbit at a fixed distance with fixed energy. In this way, the energy of the electron would be quantized. In other words, the electron could not have any energy, only certain allowable energies. So, what he postulated was that electrons can only move in certain fixed orbits, each orbit corresponding to a specific energy level. An electron can only move within an orbit without losing any energy. An electron can only move from one orbit to another when it gains or loses energy. The energy levels are much like the rungs of a ladder, but they are not equally spaced. So, what he noticed was that energy level number one would be fairly close to the nucleus, and then energy level number two was quite a big step away, and then energy level number 3, 4, and 5 were a little bit more close together. Electrons could not exist anywhere in between these steps, only on one step or on the other. So on one orbit or another, you couldn't exist in between, just like you couldn't hover between steps when you are walking up a set of stairs. So again, here is our gas discharge tube. When you pass electricity through it, what happens is the electrons become excited. When they become excited, what we think happened was that these electrons, they would start off in their specific ground state, and then they would jump to a higher energy level known as the excited state. And in doing so, they would absorb a certain amount of energy, and that absorption of energy would correspond to a certain wavelength of light. When it fell back down, it would release that energy in the form of a color, a corresponding color that corresponds to that wavelength.
In the Bohr model, the electron circles the nucleus as if it were a planet going around the sun. And with a nod to energy quantization that Max Planck dreamed up for solving the ultraviolet catastrophe, Bohr said that inside the hydrogen atom, the electron was allowed to have only discrete values of angular momentum in its orbit around the nucleus. Translated, this means the electron can occupy orbits only at certain distances from the nucleus. And Bohr simply dismissed the problem of an electron radiating away its energy by stating that it just didn't happen. Even great scientists cheat sometimes. He postulated that inside an atom, electrons only radiate energy when they jump from one allowable orbit to another. and the energy of this radiation reveals the allowable orbits. The wavelengths of light absorbed by hydrogen when white light is shined upon it, as well as the wavelengths of light when it is subsequently re-radiated, had been precisely studied at the time but never explained. Here's a sample of an absorption spectrum and an emission spectrum. By predicting the value of orbits that an electron could have, Bohr's model also predicted the wavelengths of the lines in the hydrogen spectrum. And his model was tremendously successful. It explained in exquisite detail the atomic spectra of hydrogen. When the energy of the wavelengths of the spectral lines are compared to the energy differences in orbits allowed in Bohr's atom, they agree exactly. So the quantum approach worked well in explaining the allowable orbits. But no one was certain why only those orbits were allowed.
So Niels Bohr basically stated that electrons can jump from one energy level to another. And without going into great mathematical detail, what was clear to Bohr was that electrons, when they did this jump, this is called an electron transition. And this transition from a lower energy state to a higher energy state, what happens is they will lose energy, and this energy is released as a photon of light. And this jump can also be referred to as a quantum jump. Ground state is the state where the electrons originate, and the excited state is the higher energy level state that they've been promoted to. You're going to notice here with this particular diagram, we have got 3 wavelengths of light that are specified. There's 4 actually for hydrogen, but 3 on this Bohr model. And you'll notice that red light is associated with least amount of energy. When you look at the visible spectrum, red light has low energy, and hence it will have the smallest jump associated with it. And when that jump happens and that electron falls back to its ground state, it will release that color red, a certain wavelength of red, specifically 657 nanometers. And then we will have the blue color, for instance, is associated with higher energy. So that electron made a bigger jump, and that bigger jump results in that electron falling back, a much farther distance, releasing a photon of light in that blue spectrum. Now, excited states are fairly unstable, and electrons, they fall back quickly to their ground state. What goes up must come down, and they don't necessarily fall back in all one step. So if an electron, let's say, starts off at energy level number 1, and it absorbs enough energy to move to energy level number 3, it may fall back in one full swoop and release a certain wavelength of light, or it may fall back in a series of steps. Okay, so you can see in this diagram that it may, fall back to energy level number 2 first, release a certain amount of energy and wavelength of light, and then fall back from that point back to energy level number 1. Note that electrons that are falling back to energy level number 1 are always releasing ultraviolet light, and electrons falling back to energy level number 2 are releasing visible light that we can see with the naked eye, and electrons falling back to energy level number 3 are releasing infrared light. So we can't detect ultraviolet light or infrared light with the naked eye, but notice that those jumps are all happening as well. So even though we can't see them, those electrons in that gas tube for hydrogen, those were also happening. The color that we see that's being emitted by the hydrogen gas tube, that sort of purpley color, you'll see here, this is a culmination of all the jumps that are happening. And that is the color that we will see. And only when we separate that flame color or use a diffraction grating with that discharge tube will we see the visible bands of light. But remember, all those other ultraviolet, infrared are also happening as well. The problem with Bohr's model is that his calculations only worked for atoms that have one electron. So the hydrogen atom, or helium with one electron removed, or the cation of lithium with a +2 charge. Calculations for other atoms did not agree with these experimental results. And so we have to look a little bit further in developing a new theory to help us explain where these electrons are located. This will take us into what is known as the quantum mechanic model. And here we will get a bigger picture of where these electrons are located. And it will enable us to account for some new quantum ideas. Bohr's theory was a great success because it was the start of a new approach, but now it's time to move ahead.